So we've discussed this concept of predicting spontaneity using the delta S of the universe in several sections now. We've done calculation with both the delta S of the system and the delta S of surrounding, adding them together to give us our delta S of the universe. The problem with this is that it's a little cumbersome to do that, right? You have to calculate this number, then you have to calculate that number, and then you have to add them together to get this. It's a lot easier if we can just simplify this process to calculating just a system's property as opposed to having to relate it to surrounding and getting universe. And so, in fact, this was done by chemists some time ago called Gibbs. And he basically reorganized the equation of the delta S of the universe and expressed it as a new thermodynamic property that we now call the Gibbs Free Energy. Okay, and the way it works is as follows. So we start with this equation of the delta S of universe equal to delta S systems plus surrounding. And we express the delta of surrounding as negative delta H of the system over temperature, which makes the equation now look like this. And then if we were to multiply both sides by negative t, we're going to get negative t delta S of universe on the left, and we get negative t here. We'll cancel that out and the negative as well, so we're just left with delta H of the system, and then the negative t multiplied with the delta S of the system gives us negative t delta S. Okay, this quantity is what Gibbs defined as the free energy. So that quantity now is defined as delta G of the system. And so now we have this simpler equation, which is just the property of the system called the Gibbs free energy is going to be equal to delta H of the system minus T delta S of the system. And then calculating this number tells us whether the reaction is spontaneous or not. Now, how specifically does it help us? Remember that delta G is the same as negative T delta S of the universe. So delta G and delta S of the universe sort of opposite in sign, right? So we know that delta S of universe has to be positive for spontaneous reaction. That means our delta G is negative. So in other words, delta G is negative for spontaneous processes because the delta S of universe has to be positive. Similarly, if the delta S of universe is negative, that tells us the reaction is not spontaneous. Well, the way we interpret that using delta G value is that the delta G is positive when the reaction is non-spontaneous. What about when reaction reaches equilibrium? We had discussed earlier that that means the delta S of the universe is equal to 0. If that number is 0, then the delta G of the system is also 0. So both numbers equal 0 tells us that we are at equilibrium. Using this delta G expression, it's a lot easier to kind of see how the two components of a reaction, which is the enthalpy component, delta H, and the entropy component, delta S, determine whether a reaction is going to be spontaneous or not. Okay, so we actually have 4 different situations and to look at spontaneity. And the reason there's 4 situations because each of the delta H could be positive or negative, and each of the delta S could be positive or negative. So let's look at all 4 of these combinations. We have a reaction where the delta H is negative and the delta S positive. Well, again, delta G is delta H minus T delta S. We want negative to be spontaneous, right? Negative delta G to be spontaneous. So if delta H is negative, delta S is positive. Positive times negative here with the negative T gives you negative. So that means you have negative and negative. That means you're always going to get a negative delta G if you are in this type of reaction. And so your reaction is going to be spontaneous at all the temperature that you're looking at. An example of this type of reaction is this decomposition of N2O. You can clearly see that the entropy increases here. And in this case, if we calculate the enthalpy, we also find that the enthalpy change is negative. Okay, what about if you have negative and negative? Well, in this case, our reaction is exothermic, which is good, right? We typically like exothermic reaction because that makes our products more stable than our reactant. Our entropy, though, is not great, right? It's negative. Remember, we want positive entropy change to make a reaction spontaneous, but this entropy change is negative. So that means that we have opposing factors. The enthalpy factor is favorable, but the entropy factor is unfavorable. How is that going to work out then? Well, the entropy factor is affected by temperature. It's multiplied with temperature right here. So that entropy factor then will have effect depending on temperature. So in this case, this is always negative. This number is going to be more important when the temperature value is large. So therefore, this reaction is going spontaneous at low temperature because at low temperature, that unfavorable entropy is not as significant, but at higher temperature, it's going to be significant. So this reaction is going to be non-spontaneous at higher temperature. Okay, so an example of this is a reaction we've looked at a few times here, which is just the freezing of water. So going from liquid water to solid water. From experience, know that liquid water will convert to ice at temperature below 0 degrees Celsius, but then liquid water will not become ice at temperature above 0 degrees Celsius. So what that tells you is just this statement right here, which is that the reaction is spontaneous at lower temperature, below 0 degrees Celsius in this case, and then non-spontaneous at higher temperature, which is above 0 degrees Celsius. Now, that term low and high temperature is very much dependent on the reaction itself. For some reaction, maybe below 500 Celsius is low and above 500 is high. But like for the reaction we just looked at, below 0 is low and above 0 is high. What about if we have two positive numbers? So we have an endothermic reaction, delta H is positive, and we have a positive delta S. Well, again, that factor, the positive enthalpy change, is not favorable. Why? Because now you're making a product that is less stable than your reactant. So this is unfavorable. But then your entropy is favorable because you're getting a positive entropy change. So again, how will those two factors sort of go against each other? Well, the enthalpy stays the same number every time, but the entropy is affected by temperature in the calculation of delta G. So because the entropy is the favorable one here, so at higher temperature, the entropy becomes more and more important. So then the reaction will be spontaneous at higher temperature, will be non-spontaneous at low temperature. So it's exactly the opposite of that condition, case number 2 that we just looked at. In this case, we can look at this reaction here, which is the decomposition of ammonia into nitrogen and hydrogen. This reaction happens only at very high temperature, so you need to make sure that the temperature is quite high before you will see something happening. Otherwise, the ammonia is pretty stable at low temperature. The last scenario that we can look at is we have an endothermic reaction, positive delta H, and then a negative entropy change. In this case, we have two bad factors, two unfavorable factors, right? The enthalpy is endothermic, which tells us that we're making a product that is less stable than our reactant. The entropy change is negative, which means that we're going to have fewer microstates at the end compared to the beginning. So there's really no reason why this reaction would ever happen at all. So that's why this is a reaction that is non-spontaneous at all temperature. Can you make it happen? Yes, you can, but you're going to have to find some other route aside from temperature to make that reaction happen. And we'll talk about that later on, because you could change concentration, you could change pressure. There are other things you can do. But with temperature, we're not going to be able to make this reaction happen. Okay, so I'm going to talk about this example here of these two reactions to kind of help you analyze and think through the idea of predicting spontaneity, not necessarily with any specific numbers right now, just sort of the positive and negative signs and understanding when something is going to be spontaneous and when something is not going to be spontaneous. So the question here is, under what temperature condition would the following reaction occur spontaneously? So in the first one, you're given this reaction, which is ammonium nitrate decomposing into three things here. The delta H is very exothermic, it's negative 236 kilojoules per mole. So that's favorable, right? Whenever you have an exothermic reaction, that's favorable. That makes it more likely to be spontaneous. And then the next thing we need to look at is, what about the entropy here? Well, if you look at the entropy change from the reactant to the product, look at how many gases that are being formed, whereas the reactant is a solid. So that clearly has a positive entropy change. So therefore, positive entropy, negative enthalpy, that tells us that this reaction is getting very, very favorable, meaning that it's going to be spontaneous. Now, here's the part that I really want to highlight, which is the importance of understanding both thermodynamics and kinetics. Even though this reaction is spontaneous at all temperature, you would think that as soon as you have ammonium nitrate, it would just completely disintegrate and form these guys, right? It's a very explosive reaction, as you might imagine, because you're generating so much gases here, and a lot of these gases are combustible. You can actually purchase ammonium nitrate. In fact, we use it as fertilizers, and unfortunately, it could also be used as explosive because of the fact that it generates this reaction that produces a lot of gas. So the question is, how is it that something that is predicted to be spontaneous can still exist without a reaction happen? And the explanation for that is because the kinetics of this reaction is very slow. So you remember that I mentioned before that you have to look at two things for a reaction to happen. So in this case, we know that this reaction really wants to go to the product side. However, the activation energy is so high that the reactant can't really get to it, or at least can't get to it in sufficient numbers, that pretty much this reaction doesn't really happen. We had talked about it before when we discussed the beginning of thermodynamics, that some reactions are just spontaneous but slow. Okay, and this is an example of that. So how do you make this reaction happen? Well, you need a catalyst, or you need something to get it going, which means you usually need temperature as a catalyst, like a spark. And then as soon as you get that going, then it's going to go all throughout. Okay, so this is one of those reactions that is controlled by kinetic, even though the thermodynamics tell you that it should happen spontaneously. The second reaction, let's take a look at that one. It's I2 gas going to 2I gas. Okay, so the entropy change of this should be positive because I'm going from something that is one molecule to something that is two molecules, right? Or two atoms in this case. So that delta S is going to be positive. What about the delta H of this reaction? Where I'm going from I2 molecule, which has a covalent bond between them, to 2I atoms. So I have to break that covalent bond. For me to break that covalent bond, that means I need to put in energy. So this tells me that my delta H is positive, or it's endothermic. So I have a positive delta H, I have a positive delta S. Okay, so then the question is, will it happen or not? Will it be spontaneous? This then goes back to that case number 3, where you have positive for both. So the reaction is going to happen if the temperature is high enough, because the entropy factor becomes more important at higher temperature. And the entropy factor is the one that's favorable here. So in this case, reaction is spontaneous at higher temperature. And so that's a decomposition reaction. The top one is also a decomposition reaction. And you can see that these two decomposition reactions, they require high temperature to happen. The first one requires high temperature because that's what's going to get that kinetic barrier to be overcome, to get more molecules to be able to pass through that activation barrier. The second reaction needs high energy because that's when the entropy factor becomes more significant compared to the enthalpy factor, which is unfavorable. So in fact, what chemists know in general is that when you start running a reaction at too high of a temperature, these compounds will no longer be stable, they would all decompose. And the reason is, it's just discussed in this question. Both situations basically tell you that at higher temperature, compounds tend to decompose.